Welcome to the Oxygen Alliance YouTube channel, where we bring you videos on installation, maintenance, and various trainings on oxygen equipment and devices. If you have comments and/or questions, drop them in the comment section below or write to us info@oxygenalliance.org. Remember to like our videos, subscribe to our channel, and hit the notification bell.
Hello everyone, my name is ppes and I'm a biomedical engineer for the Oxygen Alliance. I'm speaking to you live from Lilongwe, Malawi. So the Oxygen Alliance brings you oxygen talks and partner talks that are tailor-made to equip biomedical engineers and any other health professional in the health sector with knowledge on oxygen-related equipment. So I welcome you to this episode of Partners Talk. Once again, my name is ppes. And I would like to know where you're joining us from by typing your location in the chat. If you're interested in staying updated and receiving notifications for our future partner talks, you are welcome to share your email address in the chat so that we can add you to our emailing list. Presenting to us today is Joseph Isoton. So Joseph is an engineer from ppes Actors Company. He will present on a very interesting topic to us today on medical liquid oxygen and also medical gas pipeline assembly. You will have a chance to ask questions at the end of the presentation, so make sure you take notes. So without wasting much of your time, let me hand over to Joseph. Over to you, Joseph.
Good day, everyone. My name is Joseph Isoton. I'm with ppes Evaporators. What we mainly do is we advise on medical gas system and medical liquid oxygen as well. So today we're going to have a little discussion on liquid oxygen. With that, let me share my screen and then we can continue. Thank you very much. Can you see my screen?
Yes, Joseph, we can see your screen.
Good day, everyone. As I said earlier on, my name is Joseph Isoton. I'm with ppes Evaporators. And today our discussion is going to be on liquid oxygen and medical gas pipeline system. So the main topic today is going to be liquid oxygen and medical gas pipeline system assembly. We're going to look at it from the production to the patient, ensuring safety, efficiency, and quality in healthcare delivery. And our scope today is going to be introduction of medical liquid oxygen, and in short, we're going to call it mLOX. And we're going to look at the basic production principle of LOX, how we get a LOX, the effective way of transporting the LOX, the site preparation when it comes to the VIE tanks, the VIEs and the evaporators. We're going to talk about understanding the critical role of medical gas pipeline system in hospitals. What is the role of biomedical engineers and ppes technology in hospital? And then assembling and then installation of ppes and the medical locks and the safety of medical locks and ppes. Yeah, so we all know from the basis of PS system, the critical gas is the main gas is oxygen, and we actually get them from air, and air is composed of 21% of oxygen, 1% of argon, 78% of nitrogen, and other gases. So in order to get your oxygen in a liquid state, you need to drop the temperature to a minimal, to a temperature certain boiling point of the oxygen. So the main process or the main machine or the plant that is used in producing liquid oxygen is cryogenic plants. And mainly these plants are not on site, they are off site. And there are four main components of this cryogenic plant. We talk of the compressor, which mainly is the heart of the entire thing. And we talk about the air purification system, the units, and then air separation units, and then liquid storage tanks. So the compressor for mLOX system are mainly for taking out ambient air and then filtering them and then making sure that it compresses to a higher temperature and a higher pressure. And in doing so, you're going to get a large volume of air, which will be sent directly to the air purification system. But the main compressor that is normally used when it comes to this kind of plant is a screw compressor. As you can see down there, these are two screws merging together, and they are sometimes called the oil flooded screw compressors. Why? Because they are oil around them. They are normally flooded in it for lubrication and as well to cool the air that you are compressing. So mainly when the compression is done, some of this oil is carried along with the air. And then there, if there is high temperature, there is change in temperature, there is condensation. So moisture also happens to get into the air that is being compressed. And then there's hydrocarbon because of the oil, and there is moisture, and then there's carbon dioxide. So these are the things that are carried along in the air that is being compressed. So the basic idea is to try to take out all these components from the compressed air, from the PSA system. We know the principle of a compressor. So after the compression, it goes into the purification system. With the purification unit, it's just a simple but robust unit that has a lot of filtration in them. And with the air purification system, it has refrigerant water where the compressed air that is being compressed from the compressor goes into it. And during that process, the temperature drops as well. And remember, there is an air receiver tank, which also serves as a buffer for the air and also drops the temperature as well. So there is a form of reducing the temperature bit by bit. But when these compressed air goes into the refrigerant dryer, it drops further, and there is moisture carried along in the air. And this moisture, which is some kind of water deposits, is something that is not good for generation of oxygen. Remember, in our ppes system, moisture can actually spoil the zeolite. So the same principle. So the technology is designed that you need to take out the carbon dioxide, take out the hydrocarbons, and then the moisture. And if you don't do that, if you don't take out the hydrocarbons, what it means is there's a possibility of explosion when this accumulates in the liquid oxygen. And if you don't take out the carbon dioxide and the moisture, then there is a possibility of icing up in the pipelines, whereby the volume of air that is required to go into the purification system and then into the next stage of the unit will be less. So it is a typical air purification system, which looks like it's a robust, as I said, with piping and all those things. It comes with so many controls. It comes with so many valves and safety mechanism around it. So this is a typical one. So right after the purification, the air is carried along into the air separation system. The air separation system is where the magic actually happens. That is where all the oxygen is liquefied. The air separation system works using the principle of fractional distillation. There is a column. If you look at this picture, on the far right, you look at their columns, and from the top, you have your air entering, and the design is that using the fractional distillation, you are dropping the temperature from 0 to minus 185. That is where oxygen liquefied. So at that point, at the base of the column, the liquid oxygen is transported into the tank, the Isotongs, which is another storage unit. Now, with the liquid storage unit, the design is said that they are Isotongs. They are actually having both internal and external vessel. So the design is said that because of the pressurized liquid oxygen, the possibility of explosion. So design is said that it's supposed to be able to contain the amount of liquid oxygen that has been manufactured for some time before it is transported to the site to be used. So mainly this basic way of producing the liquid oxygen. Now, when this oxygen is produced, when this liquid oxygen is produced, what next? You need to transport it from one point, the main site, that is the plant, the third party who is producing it, to the facility or the hospital or whoever is buying it from the manufacturer or the supplier of the liquid oxygen. So before that, this is a typical schematic for the way it works. From the compressor, as you can see on the top left, there is a compressor. It goes into the air receiver and goes to the refrigerant chiller. That is a refrigerant water. Then the hot air is actually reduced and it goes through separations, the purifications, whereby there is heat exchange to be able to also takes out all these carbon, the hydrocarbons, take out the water, take out the carbon dioxide as well. And from there, these hot air is transported into the main heat exchanger, whereby there's a bit of heat exchange, and then it goes into the column, and that is where the magic actually happens for the liquid to be generated, and then it is transported into the liquid oxygen tank. This is what I was talking about, the molecular sieve that absorbs the hydrocarbons and then the oil and then any other things that we don't want in the air. So this is a typical one. So feel free to research on molecular sieves as well. Now, we just want to look at the technology comparison between PSA system and the cryogenic plant. For PSA system, it is mainly the temperature is ambient temperature. But when it comes to cryogenic plants, the temperature is below -183. As I said, that is where liquid actually, oxygen turns into liquid. Just like boiling water, we know the boiling point of water is 100 degrees. You are increasing the temperature of the water to get into turn to vapor. So the same way, you have a gas, you want to drop it down, you need to drop the temperature down. So the process it uses is the fractional distillation. And the purity you get from liquid and then PSA normally is between 93 plus or minus 3. Cryogenic can give you 99.5 up to 99.99 purity, which means the purity of a cryogenic plant or purity of a liquid is very high as compared to that one of PSA. And when you look at the expansion ratio, the 1 liter of liquid can give you about 798 gaseous of oxygen. So it tells you that if you have small volume of liquid oxygen, you can get more of gaseous oxygen. Now, the byproducts for PSA system is nitrogen. We all know it's a abundant nitrogen. And then the byproducts for cryogenic is also nitrogen, but they are all in a liquid state, so which means you can drop the temperature and then get the liquid nitrogen as well, get the liquid argon, krypton, and xenon, and wherever these things are used, it can be used in a liquid form. So these are basic technological comparison between the two systems. Now, after producing the oxygen, liquid oxygen, the way to transport it from one side, the main side, to other side is very, very important, very, very critical. And as biomedical engineers or as technicians, we should understand how safe or how important for you to transport these oxygen, these liquid oxygen from one point to other points. Now, in transporting liquid oxygen safely, one of the main things that you need to look at is the signages. There should be signages in around the tank that is supplying using an Isoton. There should be signages, just like transporting your flammable liquid gases like the LPG, like the petroleum. There should be signages on them to indicate that these are highly inflammable and it can cause hazard, so that people are be informed. So there should be signages both outside, in, around, wherever it is going. There should be signages around it. And then the personnel handling these liquid oxygen should be personnel that are trained for effective use of using liquid oxygen. And also during both transportation and during its delivery, there should be enough ventilation, because these are explosive. And normally there are safety mechanism around it. There are valves, there are safety relievers, and in case of high pressure, it pops out. And transporting it from one side, because you are driving it through asphalt road, you have to ensure that these things are not spilled on these asphalt, because when oxygen come in contact with anything that is flammable, it can cause explosion and fire. So all these things you need to consider that if there's enough ventilation around, then what it means is these things can be taken care of. Now from the cryogenic plant production site, you can put them on bulk tracking, that is on top. You can transport them on isotanks, and then send them to the other party or the facility or the hospital, which will have the VIA tanks and then the evaporators. And then they can decide to pipe it or maybe send it to the patient site. Or you can also transport it by filling it into cylinders and then transport it with the standing upright, with the cylinder standing upright. That is the right way to transport gases from one point to the other. You transport the gases upright, not lying down. The reason being that in case of any high pressure, it should be able to, if it pops out, and or maybe if there's anything, it should be able to still stay firm. And then all transportation should be done. If it's cylinder, you hook them up or clamp them in the car. And at the hospital, you can hook them up in the manifold system, either being it a liquid manifold or gas manifold system, and then or through cylinders, and then to the patient. So basically, this is how you produce liquid oxygen from the plant and then send to the site and then to the patient. Now, as biomedical engineers, when it comes to liquid oxygen, it is very, very important that at an earlier stage, whoever is receiving the liquid oxygen, these are the things. There are a few things that you should be able to know. You should be able to site the site that is going to install the VIEs. You need to prepare the place. You need to assess the place and things you need to do around. So selection of site installation is very, very important and very, very critical. You need to check for adequate access or excavate to make way. If there is no access, you need to excavate the entire area. You need to check if there is adequate access. You need to check if there is an escape route for the entire area. You also have to check if, in case of any emergencies, what are the things that you need to put in place. And also during the installation, because the VIA tanks are normally mounted on concrete planes, you need to ensure that these concrete planes are purely concrete, not asphalt. Because if it's asphalt and there is any leakages on the tanks, there's a possibility of explosion. So these are selecting of the sites and then excavating of the site and then checking for escape route is very important and critical when it comes to VIA installations. And also when it comes to VIA installation, it shouldn't be the proximity between staircase, because in case of emergency, people may fall over. So all these things need to be considered. You need to take a critical look as a biomedical engineer or whoever is in charge to ensure that these are not hindrances for the installation of the units. It cannot be installed under a staircase, but there should be enough ventilation around it. And competent persons are always advised to do the installation when it comes to liquid oxygen. The controls, the fittings also has to be fixed or installed at a fixed point, because if they are movable and in case of any eventuality, they can be moving and then it can create problems for the entire facility. So VIE tanks, which is vacuum insulated evaporators, this is what is actually on site. So if it's either at the hospital or it's either the facility that is engaging in the liquid oxygen. So So what there are two main types of orientation of the design of the VIs. It could be horizontal, it could be vertical, as you can see, but they all function the same. But the design of these VI tanks have both inner vessel and outer vessel. The inner vessel is actually made from stainless steel. The outer vessel is made from carbon steel. And in between the two, there is a space, a vacuum space, which is filled with perlite. The reason of doing that is to reduce heat transfer, because if there is any heat transfer which goes into the liquid oxygen, it will evaporate and then can cause you can lose most of the oxygen that is being produced. That is the reason why there is a vacuum space between the two, which is called perlite. So this is very critical when it comes to the design of the VIE tanks. Another component that is installed on the facility or at this facility is the evaporators. Evaporators are mainly for converting the liquid into the gaseous state, because at the patient side, you don't give the patient liquid oxygen, you give the patient gas. And in doing so, you need an evaporator to do that. So one end of the evaporator is connected to the VIE tank, and then the other end is connected to the pipeline with some regulations and regulators and control system. So one side connected, the liquid oxygen comes to one point, flows through, and then there is heat exchange within, and then therefore the liquid converts from liquid to gas. So this is a typical schematic, and as you can see on the far left, showing the liquid tank and then the evaporators with the components, and they always come with gauges, it comes with safety valves, comes with relief valves, comes with control valves, and a manifold to be able to control the flow of gas, the pressure that is supposed to go into the user point. So as you can see on the schematic, there are two main vessels. You have the inner one and then the outer one. The inner one contains the liquid oxygen with a relief valve on top. So in case of any high pressure, it pops out and then goes. But a vacuum is always created on top where the oxygen is, and the liquid goes down into the evaporator and then into the control panel. And then there's a superheater which actually heats to change the temperature of the liquid into a gaseous form, and it goes through regulation, either manifold and then the pipeline. If you have a pipeline in your facility, then you can send it to your facility. Another way of getting, because the liquid is at the bottom, there's a possibility of high pressure, which has already been, the temperature is high, so there's oxygen accumulated, gaseous oxygen mixed with liquid on top. And these therefore goes to the top, and if the pressure is high, it pops out. If it's not high, it goes on the right direction and then goes to the superheater, and they also convert it to the gas. So you are not losing much of the gas that is being supplied. Okay. Understanding medical gas component system. So MGPS is medical gas pipeline system. There are so many medical gas system that is always being used in facilities. Now, talking of the main manifold or the VIE tanks, talking of the PSC system or VPSC system, talking of control panel, that is the manifold, the pipeline system, the vacuum system, the terminal unit system, the area valve service units, the alarm for monitoring, they all form the medical gas component for MGPS. There are compliances and there are some regulatory bodies that we always have to be aware of when it comes to MGPS. When it comes to MGPS, you can have the ATM, the NFPA, the CSA, the AS. These are all regulatory bodies, and we have the ISO. And most people, ISO is international. Most people like to use the ISO and then the ATM. Some people also like to use the NFPA, that is at the US standard. So these are regulatory that, as a biomedical engineer, you need to be aware of. What is the responsibility of a biomedical engineer when it comes to MGPS installation? It is very, very important as a biomedical engineer to know what are your responsibilities when it comes to medical gas pipeline system. What do you need to know? What am I supposed to do in order to ensure that when it comes to MGPS, the writing is done for the facility. First thing, when it comes to MGPS, the first thing that comes to mind is piping. And copper pipe is the common one that is normally used. The reason is easy to install. It is lightweight. It prevents some fungal and bacterial growth. It resists corrosion. And transporting it actually helps you to reduce the noise as well. So the advantages of using the copper pipe is a key. So if you're a biomedical engineer, you need to know the type of pipe that is being used, whether it's a K type or an L type. It's very, very important to know that. And then also for every copper pipe, medical gas copper pipe that is being used, you should know that the tube size, which is important. You should know the date that it was manufactured. The manufacturers, normally these are all embossed on the copper pipe. With me here, I don't know whether you can see, I have a pipe, just like this. This is a twin tube pipe, if you can see. Twin tube pipe, which is end cap. So as a biomedical engineer, you have to ensure that all medical gas pipe that is coming to the site are capped, are fully capped. So if they are not capped, it's actually telling you that maybe there's a possibility of impurity getting into it. So it's always advisable to be capped, and it is only to be removed when they are ready to be used at the site. So copper pipe needs to be capped and sealed, and all other pipe fittings needs to be degreased, and they come in this form. They are sealed, and they can only be removed when they are ready to use them. Then there are identification marks on them. Then the certificate that is coming to biomedical engineers, you know, check the certificate whether they are qualified for the supply of the pipes, and then also check the thickness. Normally, the thickness is between, depending on where it's coming from, between 1 mm up to 2.5 mm. And then there are classifications that are normally embossed on the pipe, whether it's C11 ATM, whether it's BS, EN. All these things are normally embossed on the copper pipe. So the responsibility of a biomedical engineer, when a vendor is coming to supply something, you need to take your time and then check and see if these things are there. For biomedical engineer, when it comes to installation process, maybe you are not the one going to do the installation, but the third party is going to do the installation. What are the things that you need to look at? You need to look at if it's using the right hoses for the brazing work, if they are flashback arresters, if the regulators are not leaking, and then what kind of methods are they using for cleaning, and the tube cutter, when it comes to cutting of the pipe, are they using the right tool cutter, tube cutter? As a biomedical engineer, you know that under no circumstance that a person should use hacksaw, any other thing in cutting the pipe, other than using a tube cutter, because it gives a seamless cut without any debris going into the pipe or maybe showing at the one end of the pipe. And also, when it comes to the installation of the pipe works, there's something we call the nitrogen purge. The nitrogen purge. And the nitrogen, we all know nitrogen is an inert gas. And the inert gas actually helps to reduce or stop oxidation forming in and out of the copper pipe when it's being piped. When you're a biomedical engineer, you should consider check after the work, check for leak, check for pressure for 24 hours. And when this thing is done, it shouldn't drop. It shouldn't be less than, if there's any drop, it shouldn't be less than 0.2 per 24 hours. So you have to do your calculation and find out if within 2 hours it has dropped more than 0.2, then there is a problem. And then also you have to put together the carcass test documentation, which is very important for certification, to certify that all works is done and is done properly. For biomed, another responsibility is to look at the safety protocols. The labeling, when it comes to the piping, the labeling is very important. The labeling could be a text, the labeling could be stickers, could be color coding. So labeling is very important when it comes to medical gas. So it's a responsibility to find out all pipe works that is being done are labeled properly, because in the future, if you are not there or somebody is coming to do something, you should be able to identify what kind of pipe is this, so to avoid any cross connection along the way. So it is very important to properly label them and ensure that safety protocols are taken to identify the pipelines and its components. So you can also use the arrows, which is also good in conjunction with the text. The arrows actually gives the directional flow. So if it's a positive gas, you know, you're going to from left to right. If it is a negative gas, you're going from right to left. For negative gas, example is the vacuum system, and then the positive is medical air, oxygen, nitrous, and all those things. They are all positive gases. So this is actually a color coding for some area, the ISO, and then feel free to search to know the difference between some of the color codes. So for instance, for ISO, oxygen is always white, and then the US standard, the US code, it is green, and then yellow for vacuum and the white for vacuum when it comes to the US standard. So feel free to look at all these standards. So the step-by-step way of installing assembly medical gas pipeline. First of all, there should be a pre-installation preparation, which comes with marking out, sleeving, carcass installation, drilling. So these are pre-installation preparation. You need to ensure that these are actually done, and then it is based on the design that is given to you as a biomedical engineer. Though you may not be doing the installation, but you have the right to look at all this to ensure that the medical gas are installed properly. The procurement quality, you have to be involved to understand what is the vendor is bringing before any work is done. And then detailed assembly process from pipe and valves, you need to take your time and then go through the type of brazing rod that is supposed to be used for the piping, and then the techniques that is supposed to be used when it comes to the brazing. And then the best practices when it comes to medical gas integrity, you have to ensure that you have your ppes on, which is very, very important. Ensure that all these things are in place before any work is done on site. So the brazing techniques, we all know brazing is joining of two soft metals together. It could be copper pipe, any other pipe. So they are brazing rod. It could be a copper rod that is used to join the two pipes together, and there is a way of selecting brazing one. Normally these things comes from the manufacturer. This is a typical, if you can see, this is a typical brazing rod. This is how some of them looks like. It comes in different forms. It could be alloy, some percentage of alloy, 5% of alloy, and some percentage of copper as well, and we have silver based alloy as well, and aluminum silicon alloy as well. So there are so many types for considering when it comes to pipe and brazing work. So what you see is a typical effect of brazing when you don't use nitrogen. So without nitrogen, as I said, without an inert gas, and you do your brazing work, there's a possibility that your pipe, you see the oxidation that has formed on the top right, on the far top right, the oxidation that has formed outside, the same oxidation will form inside, which is on the middle portion, on the left of the middle portion. You see the oxidation that has formed. And these things, when you put in any of your gas, oxygen in it, it carries along, goes into the patient. But if there is nitrogen purging during the brazing work or introduce any inert gases, you get a clean pipe inside the inside. It is very important that during piping, nitrogen is introduced into the pipelines. So some few accessories, you have your regulators, you have your flashback arresters, you have your tube cutters, you have your cylinders, you have your brazing rods and flags, you have your lighter, which can be used in lightning, and then you have your spanners and regulators. These are some few tools. As a biomedical engineer, this is a sample or a template of when it comes to pressure tests and leak tests. So you have such a documentation which shows the section that you are being tested, the test pressure that you are testing, whether it's 2 times the nominal pressure. So if your pressure that you're going to put at the end of the project is, let's say, 2 bar, you're then twice of that nominal pressure, 2 times, so be 4 bar. You put 4 bar just to ensure that you're getting you're doing a proper leak test on the pipelines, and the number of hours that is tested is there. And then after that, you look at the pressure drop. You come back after 24 hours to check the pressure drop, and then the pressure loss, and see if it has passed on or it has not passed. And then the representative sign, whoever is in charge signs, and then the contractor also signs. When it comes to medical gases, there is something we call PTW, the permit to work system. The permit to work system is very important and critical especially when it comes to existing pipelines. And permit to work system could be a low hazard or high hazard. For low hazard, maybe if you have a pipeline being installed in an entire place and there is a leak on an outlet, you need a permit to be able to tamper with the outlet. So these documents need to be signed to allow you to go and work on the system. Because if it's a low hazard and it's an outlet, you can only go and close a valve and then change it as early as possible without interfering with any flow of gas into any other areas. But if it's a high hazard, maybe in cutting the pipelines, then you need to go through an SOPs and protocols, which is very important and critical to be able to do these work. So permit to work as an engineer, you should know that it is very important to have the PTW for all works. Area valve system. Area valve system, the main idea or main purpose for area valve system is to control area sections. So assuming you have an entire facility and you've piped the whole place and you have OT, operation theaters, you can section it, and then the area valve is supposed to, in case there's a problem at the OT, you can close it and therefore ensure that there is a flow of gas in other areas without any interferences. And also, normally most of the AVS comes with alarm panels. They come with NIST connection and gauges. So it is very important to see AVSUs. So this is a valve with a NIST system, if you can see. So this is what we call the NIST. So for oxygen, it's like this. This is an oxygen valve, and this a NIST connection. So as if you can see, normally they've written it on it. And most NIST connections, so they are there for a purpose. In case of emergency, there's a problem in the entire pipeline, you can close the valve. Close the valve, and then connect to your NIST connection, which is something like this. Connect it, and then connect the endpoint to a cylinder, and then supply the area that needs the supply of gas. Normally, most of the AVSU require power for the alarm system. The alarm system, there are two main types of alarm system. It could be a master alarm, it could be an area alarm. Area alarms are meant for areas, and master alarm are meant for the technical department or technical areas, whereby the biomedical, the head of biomedical engineer, or the technical head of technical or maintenance oversees whatever is happening within the facility. So it is important to know the types. And then when it comes to the alarm itself, it is installed in various areas, especially with the area valves. It's installed in a lot of areas depending on where it's supposed to be, and it should be close to the nurse's station or the place where it can be easily accessed by those who have been trained to work on. This alarm system actually uses transducers on the AVSU to monitor. So in case there's any high pressure or there's low pressure, it triggers. There's a pressure change, it triggers to tell you that there's a problem. And if there's a pressure drop or the gas is finished, it drops to inform you that there is a problem. So the next is terminal units. There are so many forms of terminal unit. This one is where gas is actually pumped and then sent to the patient using the flow meter. So this is a typical terminal unit. The terminal unit could be on bedhead units or pendants or wall outlets, and they are mainly gas specific. So what we say gas specific, what we mean is for gas specific, it is if you can never use air probe on oxygen probe. There are so many types of probe for which we're going to touch on that one. So these are few types of gas connection, the BS, the DIN, the AFNOR, the OMIDA. There are so many types of gas outlets. The reason why it is very critical and important for biomedical engineers to know that if you have two vendors supplying you these things, let's say one is supplying an outlet, one is supplying you flow meters, the flow meter should be compatible to the outlet, because if the supplier supplies you with a DIN probe or a DIN flow meter, it will not fit a BS outlet. So you should know the difference so that it helps you to doing the right thing. So this is a typical flow meter with a DIN probe at the end. So there are so many. This what you're seeing, the DIN one, and then there is there's another DIN hexagonal head, and you have this type from the China side, and we have the BS. This is how it looks like. The BS looks like. So every manufacturer, wherever it's coming, you need to understand whether it's an outlet, whether you're using it on a pendant, or you're using it on a bedhead unit, or you're using it on a normal wall outlet. They should be compatible. The flow meter and then the outlet should be compatible. There's a right way of using the flow meter and the humidifier just to regulate, because you are giving out pressure in the pipelines, but you're not giving pressure to the patient. You give flow. So it's very important as a biomedical engineer to know that how much flow are you giving to the patient. It's very important. And what are some of the safety mechanism when it comes to MGPS? You should have your ppes whenever you're going close to any pressurized item. It's very important to do that. No flammable, no naked distance. Report any leakages that you see around. It's very important. When it comes to LOX, we also have to think of the future. What is the future? In this part of our world, we know it is important how COVID came and then showed us so many things. We've encountered the need for oxygen through concentrators, through ppes system. And for LOX oxygen is something that we should embrace. So the next trend and future trend is for government to get into it, which because the volume is very is good. The maintenance for facilities is actually less as compared to having a PSA plant in your facility. And emerging trend innovation, these things can be connected using clouds, get information from your cloud through text messages, getting it from on your phone. You can check your working remotely to see where the problem is coming from. So all these things are future trends and innovation that are coming up for when it comes to LOX system. These are things that we've looked at today. We've spoken about the production of LOX. We're talking about the transport, the safe way of transporting LOX. The safe way of installing LOX and handling LOX. And then the key thing is the responsibility of Biomed when it comes to MGPS and then LOX system. Thank you very much. And the floor is open for questions.
All right, thank you very much for this wonderful presentation, Joseph. This is now time for questions, as he has already said. Feel free to raise your hand or type your question in the chat. I will mention your name and give you a chance to ask. So, go on. So we have a question in the chat. Olem is asking, let me assume oxygen, gas oxygen demand consumption for a specific healthy facility is 30 Newton cubic meters per hour. I want to procure and provide oxygen through a liquid oxygen source. So how do I calculate the volume of the tank? Size, vaporizer, in brackets single, double, installation site dimensions, for how many days used the oxygen, and the other requirements. So I hope you got that question, Joseph.
Kim.
Yes.
Yeah, I think at the point you break off. If you can come out with a question again, please.
All right. So there is a question from here.
Okay.
He's asking, let me assume gas oxygen demand consumption for a specific health facility is 30 Newton cubic meters per hour. I want to procure and provide oxygen through the LOX source. So how do I calculate the volume of the tanker, size, vaporizer, installation site, and dimension, and for how many days is the oxygen to be used, and other requirements?
Okay, thank you very much. I think this question is deep. When it comes to sizing, it's very important. When it comes to sizing of VIE tanks and then the consumption rate. First, you need to know your consumption rate at your facility, and then you can, based on that, you can determine what is the capacity that is required. And if you have to do a VIE tank, there are specifications that you need to go through with the consultant or the manufacturer to be able to size it properly for you, in order for you to get the required volume that is needed within the facility. And as I said, this is a deep question, because you need to do a lot of calculation to be able to determine how much is to be consumed and how much do you need to be able to sustain you for a period of time. Yeah.
All right. I hope that answer was clear enough, Arem. So we have 3 hands from Emmanuel, Millicent, and the other person is missing here. So we'll take 2 questions at once. So Emmanuel, go ahead, and we'll go to Vincent.
Thank you, and thank you for the wonderful presentation. My question is, I've noted that in the explanation, there was a statement to imply that you're using an oil compressor, and I was just wondering, is it not possible to use an oil-free compressor, considering that the waste that we are generating by using the oil compressor, we also have to remove them in the second stage? And the other question is, how does this system compare to the PSA system, where we have a PSA plant and we're also generating oxygen? Of course, I know basically that maybe the percentage of the concentration of oxygen that we're generating can be different, but I was more interested in the maintenance aspect of cost. Thank you.
Thank you, Ima.
All right, so I think we should also take another question from Ishmael in the interest of time. So go ahead, Ishmael. All right, so you can take that question, Joseph.
Yeah, thank you very much, Jim. Yeah, the first question came from Ima. Ima was asking the comparison between the oil-free compressor and then oil-lubricated compressors. Yes, of course, you can use the oil-free compressors. We have the VSD screw compressors, which are not mainly oil-free. What it means is there's oil, but it doesn't come in contact with the screws. It can be used. But when it comes to the oil-flooded, the idea is to get large volume. And comparatively with our down here, especially in Africa, VSD is a challenge for most facilities when it comes to the maintenance and then the cost. So a lot of people like to use the oil-flooded one as compared to the oil-free one. But of course, you can use oil-free VSD compressors to produce your gases. But I have never encountered piston compressors for production of because the volume that is required when you compare that one to piston compressors, it is less. So normally screw compressors are required. So you can use either oil-flooded or oil-free compressors, but it should be a VSD type, which VSD screw compressor. And the second question was a comparison between the PSA and then LOX in terms of maintenance. Yes, as I said in my submission, the maintenance for a PSA system is expensive because you are aside buying spare parts for your compressors, your dryers, your PSA system. All these things involve cost. So the cost implication when it comes to PSA is high. But unlike LOX, a facility, all that you have is your VIE tanks and then your evaporators. no electricity, only few electronics for maybe monitoring, which does not consume much. And maintenance are to check leaks and to change seals and all those things. So it's not expensive when it comes to the maintenance aspects of the considering the PSA and then the LOX. PSA maintenance is expensive, and then the LOX is less expensive. Yeah. Shim.
All right. I hope that was clear enough, Emmanuel.
Very much so. Thank you.
All right. We have more questions in the chat. So Kumbo Kalua is asking, can you please elaborate more on brazing? And another question is asking, okay, he's asking if we'll share the presentation. So the presentation will be available on Auction Alliance's YouTube page. So keep an eye out. It should be available from next week. So you should keep an eye out on that. So that's the first question, Joseph. And there's another question from Lok Musoli. There is a qualification tool which calculates design by part. I don't know if this is a question. All right. So Millicent is asking here, thank you for the wonderful presentation. Just wondering if the audience can be informed of some of the sites where you can learn more about the liquid oxygen, the mLOX, and also the MGPS as indicated in your last slide. So
okay. Yeah. Yeah. Ishmael wants to know more about the brazing. Yeah. Brazing, as I said, is a technique for joining two soft metals. Example, like a copper to copper. It could be copper to brass. So, but there are ways of brazing, and there are accessories that are used in brazing. So you need a gases to braze. You need oxygen. That is a common one, oxygen, and then acetylene. That is a common one for brazing. And then, of course, you use your nitrogen or your inert gas for your purging when it comes to, in terms of medical gas. So these are the gases that are commonly used. You can also use propane, where you can use propane to do your brazing as well. So when it comes to brazing, you have your accessory like the rod, the brazing rod. And then maybe if you're joining two different metals like a copper and then a brass, you may have to introduce in your flux for your brazing. You wet the flux around the joint, and then you light a fire. And the proper way of, a lot of people uses normal matches, but the best, because of safety, is to have a lighter. There is a lighter, I don't know whether you can see. There's a type of lighter that is used for fireworks when it comes to brazing. And then you join the two pipes together with the air fittings, and then you braze. So you have to open your acetylene on the fire, regulate it, and then do same for the oxygen to get a blue flame, the required flame that you want, depending on the thickness of the copper pipe. If it is too thick, which means the fire, you need to increase both oxygen and then acetylene. So based on your mixture, you get the blue flame that is required. In my one of my slides, I think slide, yes, as you can see, it is clear like a blue flame. So this is how it looks like. This is how your brazing flame is supposed to look like. And then you use your rod, melt the rod around it. Thank you. Yes, of course, the slides come. There are sites that you can get other information on liquid oxygen, but maybe not in depth because of the sensitivity of it. But as MGPS, that's something that we do. We advise and we consult. So if you hop into our site, we can actually help you on that as well. Yeah. Yeah, Chim. I don't know whether if you've missed any other question.
So there's another question in the chat as well. Patalag is asking, if someone doesn't have the nitrogen gas, what other way he or she can use instead of the nitrogen gas?
Yeah, so nitrogen gas is an inert gas. It's an inert gas. So you can use there are so many inert gas around. You can use argon if argon is expensive. If you don't have argon, nitrogen is the cheapest and it's readily available in a lot of places. Most areas have nitrogen plants that they fill bottles for nitrogen. So it should be easy to get it. Without that one, when it comes to medical gas piping, it becomes very difficult because you need to get a clean pipelines for it. Down here, I've witnessed people just putting in pressure and then blowing it up, and then after that, but there will be some deposit of carbon inside the pipe. So the idea is to eradicate all carbon deposit in the pipe. So nitrogen should be resolved in your local area. Try to find out where you can get a nitrogen for this work, or you can see the best way of purging it out. But it's mainly on oxygen, but oxygen and then air, medical air. But other gases, it is not strictly on that. Yeah. Thank you, Jim.
Thank you, Joseph. So, Tadaruka, was that clear enough? So the silence means yes. We have another question. So this one is coming from Harold Chipepo. He's asking, thanks for Joseph for the wonderful presentation. My question is, how can we clean the medical gas pipelines as part of preventive maintenance?
So when it comes to maintenance, ppes, preventive maintenance on medical gas pipelines, in cleaning the pipes, unless of course where you've installed the pipes it's coming in contact with so many things that they need to use the fine tin material in cleaning it, and it should be oil free. But maintaining of pipelines is leak test, because pipelines after the brazing works, it can be there for some time, but during your preventive maintenance, you can use oil free liquid soap or detergent to check leakages all around. That is one of the few maintenance you can do on pipelines, is to be able to know if there are leakages around or in any of the joints. But the cleaning, you have to use a fine material. There is this fine material used in cleaning copper pipe that you can use to clean the entire pipelines once again to do it. Other than that, you don't need to clean the pipe during maintenance unless you see some deposit or the pipe comes in contact with things that are not supposed to be there. That is where you have to do the cleaning on the pipe and then rectify the problem where the thing that is coming in contact with the copper pipe. Yeah. Thank you, Jim.
All right, thank you so much, Joseph. I see that we have there are a lot of questions, but in the interest of time, we will not be able to cover them all here. We'll compile the question that you have asked in the chat and make sure that you have answers in your emails. So for further question, you can email us at info@oxygenalliance.org. So this marks the end of this call. Thank you, MGPS actors, and of course you, Joseph, for making time to share with us on medical liquid oxygen and also the pipeline assembly. It has been an educative session indeed. Thank you all for attending this talk. Goodbye.
Bye.